Yeah, but shooting's okay, especially if you do multi-shooting. Then you can kind of shoot one way and only lose exponential, have exponential on small intervals. Oh, yeah, that's tricky going on. You need the asymptotics out there. All right, so I guess we should probably.
Oh, yes.
Okay. So, Elisabetta, can you hear me?
Yes, perfectly.
Okay, great. All right, so I think we should get started with our afternoon session. So thank you for coming back after lunch right away. So our next speaker is Elisabetta Rocca, and she'll talk about optimal control and early states reconstruction and phase field models for tumor growth.
Thank you very much for your introduction, and sorry for not being able to be there. And so it would have been a pleasure, but I couldn't for some teaching and family reasons. So I'm happy to at least to be online with you. Today I would like to speak about some joint project that we have in together with some colleague in my department, the University of Pavia in Italy, and also to some colleagues abroad. So I will show you the collaborators later on. So what we are speaking about, optimal control problems in phase field models. And the application that we have in mind is the one related to tumor growth. And so as you can see in the picture, we will have different type of tumor growth. This one in the picture is the prostate tumor growth, but we will also speak about brain tumor growth. So they are quite different, and we will use different models, but we exploit some common techniques in both cases. So let me start. So this is the outline of the talk. So I will start with a brief introduction to phase field models, in particular for tumor growth. Then I will start with the two type of models I told you. So the first one is the prostate cancer model, and the second one is the brain tumor model. And in both cases, we are interested in different topics like well-posedness of the resulting PDA system, which underlines the model. But also simulations in order to see if our models are compatible with reality, and optimal control in the sense of optimal therapies, but also inverse problem. And this is a bit more difficult to explain in the case of tumor growth. So let me go on and explain it later. For brain tumor, we will have a different model. And for this model, which is a fourth order in space model, we will also tackle the problem of inverse problem, and in particular, the reconstruction of early stages of the tumor. And I will try to convince you about the clinical interest of this topic. And then I will conclude with some further open problems. So the motivation is quite clear, and so the tumor that we are dealing with are the so-called solid tumors. So maybe I'm more in the first part of the title of this workshop with respect to the second. So there will be no fluid, but just solid tumors like prostate or brain tumor. And the dynamics of this tumor are described by partial differential equations, as I told you, which is the topic I'm interested in. And more in particular, they are related to the famous, let's say, Allen-Kahn and Kahn-Hilliard equations, which are coupled to other equations for the chemical species. And so the end goal of this approach, which we call mathematical oncology, because we are working in oncology, but from a mathematical perspective, is to provide a patient-specific tumor growth model in order to inform better clinical decisions. So not to have the same therapy for all the patients, but just to have some therapies which are adapted to the data of a single patient. And so there are several possibilities in order to work on this kind of problems. For example, one could try to tune the model parameters because there are several parameters in the model. This is useful, but it is also useful to reconstruct specific earlier evolution stages of the tumor in order to better predict the evolution of the tumor. And this is what we are actually doing, and this is the so-called inverse problem. However, these problems, the inverse problem, as maybe you know, are quite difficult to tackle from a mathematical point of view because of their intrinsic repose-ness, because they are backward in time inverse problems, but we will use some approximation technique and also some simulation will help us in order to solve the problem. Okay, so it is important for an application for clinicians to locate both the areas where the tumor started growing and also the shape of the tumor at the beginning or in a previous stage in order to better predict its evolution. So our contribution goes in this direction. So this is our goal, the clinical scenario for the inverse problem. So we have, let's say, some MRI at some time capital T. So you see this ball or this ellipse in the center is the tumor. So the red color denotes the tumor cells, and the blue color the nutrient, let's say, so the healthy cells. And so at time capital T, we have some MRI. What we are doing is to reconstruct an earlier tumor stage. So at a previous time that we call, for example, T equal to 0. And then we start with this initial condition for our PV system in order to solve the problem and to predict better the dynamics of the model in order to help the clinicians with the clinical decisions, so therapies and so on. So why prostate cancer? Actually, prostate cancer is one of the main health problem worldwide. And as you can see, it is the third mortality type of tumor in Spain. My collaborator, Guillermo Lorenzo, comes from Spain. That's why we have this datum. This is the second one in USA, and it is the fifth in the world. However, it is quite confined, the tumor. So most of the time, this tumor is not so dangerous as the brain tumor. And so there are better possibilities to try to help clinicians in the clinical decisions here. So what is the mathematical oncology perspective with respect to the current and the standard oncology? So we don't try to change prevention or regular screening. These are the same. So PSA test, for example, digital rectal exam, these will always be the same. What we are trying the place where we are trying to intervene is the moment of diagnosis and staging. So in particular, we try to construct a computational anatomic model. So let's call it a digital twin of the patient using the MRI data of the single patient, which we have a project together with the Policlinico San Matteo in Pavia. Then we try to select the parameters which are responsible for the evolution of the model to construct the growth model and to simulate in order to have our evolution to try to foresee the evolution of the tumor in future time. And so to design the optimal treatment. So this is optimal treatment in contrast with the standard treatment, which is not optimal in the sense that it's not tailored on the patient. And then there is also the follow-up, so modeling a simulation, which helps us in following the evolution of the tumor for the patient.
Elisabetta, may I ask a question? Sorry.
Sure, please. Sorry, I cannot see the people, okay, but I can hear you. I can hear you.
I don't quite understand why you have to go back in time. I mean, if I have the MRI of the tumor now, why don't I solve the forward problem? Is this to estimate the parameters or why do you go back in time?
Okay, so this is okay. One could also go forward. This was the first problem we tackled. The second problem was these inverse problems to go back because this was a request of the clinicians. They told us that when you see the tumor is already advanced, so it's not in this starting stage, you know, because okay, maybe you have already the tumor is growing in your body and you don't know. And so for them, it's important to know how the tumor was before. So not, let's say, at the beginning, but okay, how it started to grow. And from the position, from the shape, and so on, they can better foresee what will be the future of the tumor, the evolution of the tumor. And this is what we try to do. let's say, to start from these initial data, and then to construct the model starting from this, and I mean to foresee the evolution of the tumor starting from this new data. So that's why we.
Yep. Thank you.
You're welcome. And okay, so let me come to the equations. Then I will go back to the inverse problem later. Okay, so our model comes, as I told you, this is a model which couples Allen-Kahn type equation. This is the first equation you can see on the screen. And the variable here is called phi. Phi is the order parameter of the system, so the phase field parameter, let's say. And you can distinguish in this picture, which is a real picture, of a tumor. So we have phi equal to 1 means that we are in the black zone, which is where we have tumor. Phi equal to 0 means we are in the healthy tissue, so in the gray zone. And the evolution of the phi then is described by this equation. And in particular, I speak about a phase field model and not of a sharp interface model, because I consider the fact that phi can also take values in between 0 and 1. So my order parameter is not just or 0 or 1, like in the sharp interface models, but it can take also the intermediate values, assuming that, for example, there is an interface which has a depth which is not 0 here in between the two phases. And in this interface, we can assume that we have both phases, so both tumor and healthy phases. This is the same also for other models, not only for tumor growth models. There are phase field models in different frameworks, starting from the Stefan problem. Then this phase field model have been introduced in the past and studied a lot in the literature. And now we try to apply it also to this kind of application, medical application. So the evolution equation is this one, which is called the Allen-Kahn type equation, because of what we have the Laplacian of the phase phi. This equation, you can think about it as coming from the gradient of an energy. So the evolution of phi goes into the direction of minimizing an energy. And in the energy, you have the gradient of phi square, let's say, times a coefficient, which this coefficient d denotes something which is proportional to the length of the interface. Gradient of phi square, then there is a potential f. And this potential f, you can see here the shape. This is a kind of double well potential, which has the two minima in the two phases, phi equal to 1 and phi equal to 0, which are the tumor and the healthy phase. So this part of the equation, so the derivative of this part of the energy with respect to phi, brings the system towards the minima, so towards the pure phases, phi equal to 1 and phi equal to 0, while the gradient square prevents the system from having too many jumps in between the two phases, phi equal to 0 and phi equal to 1. So it regularizes somehow the system. And so these two are competing, and depending on the parameters, you have different evolution. Then in this equation, this Allen-Kahn equation is not decoupled, but it is coupled with the evolution of the other two parameters, which are sigma and p. Let me go first with the sigma. The sigma is the proportion of the nutrient. The tumor will not grow without nutrient, in the sense of, for example, glucose or oxygen, which is contained in our blood. If there were no nutrient, the tumor would die. And indeed, you can see that the nutrient is here in the right-hand side of the equation. The more there is nutrient, the more the phi is growing. The derivative is growing, and so this means that less nutrient we have, less the phi is growing the same. So this coefficient chi is called the chemotactic coefficient, while the coefficient A that we have here is called apoptosis coefficient, because this means that the tumor cells are dying by some natural process, internal process, not due to the nutrient, let's say. So these two equations are coupled. The nutrient equation satisfies a reaction diffusion type equation, and it is also containing the phi. So the nutrient is consumed by the tumor. So the more there is tumor, the less there is nutrient, because the tumor is consuming nutrient. I also put here some coefficient gamma S, which is some pre-vasculature of the system, and some source S that we will see what will be in the future. So this will be one of the control parameters, one of the therapies, but I will introduce it later. Then, since we are speaking about prostate cancer specifically, it's needed to have another equation for the prostate-specific antigen, the PSA. So this is what you compute, what you measure when you do blood exams, and you calculate actually what you measure is the integral of this P over the domain omega, which means that this is a density of PSA, and the density of PSA is also evolving according to the tumor cells. And indeed, this is one of the variables that we would like to keep lower than some threshold. In your blood exams, you always verify that your PSA is lower than some threshold in order to be safe. Okay, then we have some boundary conditions. We could take 3 Neumann homogeneous boundary conditions, but we choose to take phi equal to 0 because this was coming from some previous model by our collaborator Guillermo Lorenzo and others, Hector Gomez and so on. And so this means that the tumor is confined inside the domain of the prostate. This is quite common for prostate tumor. Otherwise, one could take no flux boundary conditions like for the nutrient and for the PSA index. Okay, so this is the growth of the tumor depending on the parameters. So as you can see here, the tumor is spheroidal. These are the first one in the first line are the true imaging, and also the second one, and the third one are the one reconstructed by simulations. The tumor is spheroidal as soon as these parameters that I introduced before in the equation chi, the chemotactic parameter, and the apoptosis are small. While the tumor becomes fingered, which is the reality, let's say, in real tumors, when these parameters are high, because these are the parameter which causes the growth of the tumor. So what can we do against the tumor? As you know, therapies. So what we can first investigate is the so-called control problem. The controls will be the therapies, and what we want to control are the growth of the tumors, or this phi variable, let's say, or the volume of the tumors to the integral of phi, and also the PSA index, which should be below some threshold. So the most commonly used therapies nowadays are chemotherapies, so cytotoxic drugs, and they obstruct the growth of the tumor in preventing the tumor to proliferate, and they promote the death of cells, tumor cells. So this means that mathematically modeling speaking, it's meaningful to have this a function of this type depending on x and t, on space and time, in the phi equation. So these kind of parameters that we had in the phi equation, they should be the control which inhibits the tumor growing. There are also other therapies, for example, anti-angiogenic therapies, which basically prevent the nutrient to grow. So the less there is nutrient, as I told you, the less there is the tumor is growing. And so what these therapies are acting on the vessels, on the blood vessels. And I will try to show you how we can include them in the model. This is the S term that we had in the nutrient equation, the S equation. Or one could try to combine both therapies. So one of the main goals of our first work was to see which differences you have if you take just one therapy or you combine both therapies. And so we propose a model for PSA growth, which is the one you have seen before, but we introduce cytotoxic and anti-angiogenic drugs as a control. And what we want to control, as I told you, is the phi variable and also the serum PSA. Okay, so the derivation of the model. So I will try to convince you that this model is good. Let's say this is a kind of generalization of the previous equation you have seen before, the Allen-Kahn equation. So we can take something more general. Let's say the previous one was the easiest one could imagine. what we can take is always the Laplacian, let's say, the regularizing term. We are Laplacian people, so we cannot get rid of this Laplacian. We have the double well potential, which is competing with the Laplacian. So the F term is always similar to the one. We can also generalize it from mathematical point of view with different powers. But okay, this is the prototype. And then we have this term on the right-hand side, which includes a new term, the U. The U is the function depending on x and time, which is a datum of the problem. And then in the optimal control, this will represent the optimal control. So we want to control the tumor using this, varying this U, which represents cytotoxic chemotherapy. The M of sigma is a bounded function of the nutrient, which, for example, one can take in this way. I will show you a picture in a moment of this function G and of its derivative so that you can be convinced that this represents what we want. This H of phi, again, is an interpolation function in between the values of phi. But let me show you the picture. So the central picture, the blue one, is the G. So the G is the double well potential minus this function depending on the nutrient and the phi. And in particular, what is doing the G, if the nutrient is M of sigma is proportional to the nutrient because it was their tangent, if you remember. So if this sigma is I, then you have the blue curve, and this means the nutrient is I. You have that the most favorable phase is phi equal to 1, which means that we are in the tumor phase. So the more you have nutrient, the more the tumor phase is the most favorable one. While if M of sigma is negative, which means sigma is low, then you have the light blue curve, which means that 0 is the most favorable phase when you consider the evolution equation, which drives the evolution towards the derivative of this function G. So 0 means healthy phase. Okay, this is without therapy. So with U equal to 0, and the first line. The second, in the pink line, in the pink column, you can see the derivative of the G, and this is the derivative of the double well potential. In the second line, you can see what happens if you put some therapy, for example, some constant U, beta C. And then if you put some therapy, you are lowering the values of the minima, and in particular, the most favorable, what we want to do is to have that the most favorable equilibrium is phi equal to 0, which means healthy phase. Okay, not one anymore. Even if the sigma is high, the most favorable phase is the healthy phase. So this is how the U intervene in the equation in order to do this work, the therapy work. For the sigma, we have a direction diffusion equation you have seen before. What we introduce here is the S, the therapy, and this is the anti-angiogenic therapy. Okay, which means that we prevent the blood vessels to grow too much in order that we keep the tumor smaller because there is less blood coming to the tumor. Then the prostate index equation is the same you have seen before. Actually, what you measure in your blood exam is the integral of the prostate index, the density. And so then which also satisfies an ODE, which is this one. And then what we want to minimize is this integral. What do we take for our simulation as U and S? This is not needed for the analysis, but for the simulations, and this is reasonable because the therapies usually are given in cycles. And so you have, for example, the time TCI is the times of drug delivery. The H is the Heaviside function. So when T is greater than TCI, this is equal to 1 and T is 0 when smaller. So you have some therapy just at some time, and then you stop. And then you have some coefficient in front, this exponential times this constant. This is related to the cytotoxic effects and the drug dose. And then you have several doses. So this is the number, NC is the number of chemotherapy cycles. Usually you do some cycles, then you stop, and so on. And the same for the anti-angiogenic treatment cycles. So for example, you can imagine for our simulation to have 10 doses, 1 dose every 3 weeks. Then, okay, let me come to mathematics. So this is to an analysis of the problem. So this is our phase field model, coupling the 3 equations with the boundary condition, and also we have initial condition as usual. So for the moment, the initial condition are fixed. So we are just dealing with optimal control with respect to the therapies. So U and S are our optimal controls. We have 2 optimal controls. One is in the phi equation and one is in the sigma equation. And first, we have to solve the problem. So this was our first work in collaboration with a colleague of mine, Pierluigi Colli at the University of Pavia, Hector Gomez and Guillermo Lorenzo, who are also responsible for the first model you have seen in the first slide. And then also Gabriela Marinowski from Bucharest, our colleague, and also Alessandro Reali, who is an engineer and actually is now the president of our university in Pavia. And so, like Guillermo Lorenzo, they are all engineers that now are working on this kind of problem too. So first, what do we have to prove? We have to prove existence, well-posedness of the system. So this is the basic, the starting point. And the system is also compatible without our conditions. So the phi is really, we can prove that the phi by some maximum principle is in between 0 and 1. Due to the shape of the equation, this is possible. And we can get some boundedness of the 3 variables, in particular sigma and P are bounded. Sigma, the nutrient is non-negative, the nutrient proportion, and also the PSA index. And in some cases, we can also keep them lower than 1, but in general, they are bounded if we don't impose any other condition. And that they say in these spaces, you don't have to read all these spaces. H, this is the classical Hilbert triplet. So H is L2 of omega, our space domain. V0 means the space H1 with the Dirichlet homogeneous boundary conditions, while B is just H1. And W is the space H2 with the Neumann homogeneous boundary condition. Sorry, W0. And W is just H2. And so this is the classical parabolic regularity. So the time derivative are L2 in with values in L2, and the variables are L infinity in H1 because we have the gradient square in the energy. And then we had some regularity from parabolic, from the parabolicity of the system. Let me come to the optimal control. Having the basis, which means we have well-posedness of our system, then we want to tackle the optimal control problem, which means we want to minimize some optimal control functional subject to our state system. So our control functional is a function of the 2 controls, U and S, where phi, P, and also sigma is not involved in this tumor, in this control functional, but okay. They, phi and P are the 2 solutions of our equation with the data U and S, our state system. So this control functional is of tracking type, let's say. So in particular, we want to control the most important terms are the one in orange. So we want to control the final distribution of the tumor phase. So we wanted it to be closer sufficiently to a desired distribution phi omega. Phi omega is our target. And we assume to take the L2 norm for simplicity. One could have some LP norm. We need convexity. Then we want to control the total volume of the tumor at time t, and the total volume of the tumor is the integral of phi. And as I told you, we want to keep the integral of P, the PSA index, lower than some threshold, which is our target P omega. That's why here we put the positive part. So this means that this is minimized when P is less or equal than P plus. But we don't want to apply too much therapies because this could also, as you can imagine, damage vital organs. So we also put these 2 regularizing terms here, U square and S square, U and S being the controls, which belong to the set of admissible controls. So it's reasonable that they are bounded. We don't impose infinite therapies. So this is one type, one possibility, one choice of the optimal control function that we can deal with. Then, as usual, in order to solve the optimal control, we need some adjoint system because we have some necessary optimality condition But in order to get rid of the linearized variable, what we need in the optimality condition is the adjoint system. You don't have to read it, it's just these are the adjoint variables. W is the adjoint variable to phi, Z is the adjoint variable to sigma, and Q to P. And as you can see, this is a backward problem. So we have final condition, and in the final condition, you just get the derivative of the functional J with respect to phi, the blue one, with respect to sigma, there is no sigma in the function, so it's 0, and with respect to P in the last term. It was linear in P, so here you just have a constant. Okay, so which are our optimality conditions? We can formulate them in a synthetic way in this way. So if you have an optimal control, first of all, we have, I didn't write it down, but we have a result saying that there exists at least one optimal control. And this is done with the standard methods of calculus of variations. But then we want to show first order optimality condition, necessary optimality condition. And these are the first order necessary optimality condition. They are two because we have two controls. And they can be formulated in this way, which this is an abstract way, but I also show you the concrete way. So you start, the optimal control is 0 on the set where this W is the adjoint variable to phi is smaller than 0. And this is the H prime of phi times W on the set where this is in between 0 and U max. And it is just U max on the set where this is greater than U max. So this means that you have the projection on the set of admissible control, which is bounded. And so you don't have just one admissible control, but you have a projection, which is split in these three ways. And the same for the S star, so the optimal anti-angiogenic therapy, which involves Z, which is the adjoint variable to the nutrient, to the sigma. Okay, so let me show you the simulations now done in the way you have seen before. So first we start with an untreated mild tumor. So a tumor where you have low proliferation, rho, and low apoptosis, and a small difference in modulo of the two. And you don't treat it, so you have U and S equal to 0. Then what happens to the tumor in time? I hope you can see the simulation growing. So the tumor is growing. And so on the left, you can see the picture of the tumor. So phi equal to 1 is the red one, which means that you have tumor. And phi equal to 0, you have healthy phases. On the right, you have the nutrient. So as you can see, the tumor is continuing growing. And okay, so this is the case of untreated tumor. What happens if we have an aggressive tumor? With an aggressive tumor, which is high values of rho and apoptosis, the tumor is growing more, and in particular is starting producing branches, as we have seen in the second probably slide. Okay, so it started producing branches. Okay, what happens if we introduce drugs, so cytotoxic drugs or anti-angiogenic therapies, or we combine both therapies? I will try to show you that for especially for aggressive tumor, the best is to combine both therapies, as one can imagine. So if you just have cytotoxic therapies, what happens is that the tumor is reducing for some time, as you can see now in the picture. You just apply U and S is equal to 0, but then it's growing again. This is the aggressive tumor with just U different from 0, so cytotoxic therapy, but no anti-angiogenic therapy. If you just put anti-angiogenic therapy, but not chemotherapy, what happens again is that the tumor is reducing more, let's say, in a different way with respect to what happened before, but then it's growing again. While if you combine both U and S, so the two therapies, then this is the good news. Obviously, this is a simulation, so what we can see here is, and you can see it also on the picture, it's going to 0. The tumor volume is the one in brown, and the PSA serum is lower than the desired value. This is a simulation, okay, it's not a reality, but okay, this is what we want to do. So the goal we wanted to achieve. So the best is the combination of the two therapies. So this was our first goal, to solve optimal control problem. The second goal was inverse identification of the initial data, the things I've mentioned before. The system is basically the same, so I don't comment it anymore. What we want to do is to solve the so-called inverse problem of identifying the initial data, phi 0, sigma 0, and p0, starting from a measurement, so an MRI at the time capital T, let's say, and a datum for the PSA index at the time capital T. And this can be used in order to calibrate better the therapies on the patient. And in this case, we consider no therapies in the sense that we start from this problem with no therapies, and then we calibrate the therapies later on when we have identified the initial data. So, as I told you, we have to reformulate our inverse problem. So we have that our data are now phi measure, sigma measure, and p measure. So the value of phi, sigma, and p at time capital T, and what we want to reconstruct are the initial data. The Hilbert spaces where we do everything are always the same, the Hilbert triplet we have seen before. Okay, so first what we have to do, we have to prove the differentiability of the solution operator, which maps the initial datum to the value of the solution of capital T in L2. And we introduce the set of admissible initial data. So admissible initial data means this for us. So phi 0 is in between 0 and 1, sigma 0 and p0 are bounded. This is also a closed convex set in the space H1 for the three variables and then infinity, and this is good. And we can prove that this R is Frechet differentiable. Basically, we use the results we had before for the optimal control problem to prove that it is Frechet differentiable. And the Frechet derivative of this operator is nothing else than the solution of the so-called linearized system. As you can see, this is a linear system in the variables y, z, and p, and we have linearized around the points phi bar, sigma bar, and p bar. So then we can prove backward uniqueness. This is the first step. So if we have that the three solutions are equal at the time capital T, then we can prove that the three solutions are equal for every, here there is a t, small t missing, for every t in between 0 and capital T, and in particular they are equal at the beginning. So this is backward uniqueness for our operator R. Then we want to reconstruct initial data. And what we can prove following the, let's say, old paper by Isakov of 2017 is that if we have two solutions corresponding to triple of initial data in the set of admissible data, then we have this older continuous estimate with some exponent lambda that can be computed here. And the gamma just depends on the parameter of the system, the apoptosis and so on that you have seen before. And here we have this estimate, this older continuous type estimate. We can also get some logarithmic type estimate, but are assuming more regularity on the initial data. So if we assume that the initial data are bounded also in H1, not only in the set of admissible control, which was just L2 with L infinity, let's say, then we can also prove more regularity for the solution, and this implies this logarithmic S-type estimate. So we have that the difference of initial data can be bounded by the logarithm of epsilon, where epsilon is the somehow proportional to the difference of the two solutions at time capital T, the square root of 1 over the square root of the logarithm of epsilon. And so this logarithmic estimate, unfortunately, is the best we can do, but it is not useful in application. So what we would like to have is a Lipschitz stability estimate. But this we can do only under some restriction, but as it's somehow usual in inverse problems, on the initial data. In particular, if we have that the initial data are in a finite dimensional subspace of H1, which can be this cap K, then we have Lipschitz continuity, Lipschitz continuous estimate, depending only on the parameter we have seen before. And this is good for simulations, because for simulation, usually you discretize the problem, and in any case, the data are in a finite dimensional subspace. And so this for simulation is okay. Then we do numerical reconstruction. So what we do, we don't solve directly the problem because this is an imposed problem, but we introduce the so-called Tikhonov approximation. So we solve the minimization problem where we want to be close to this phi mesh. So we minimize the functional where we have the norm in L2 of pi at capital T minus phi mesh square. So we are close to the phi mesh in the L2 norm. The same for the sigma and for the P. And then this minimum problem admits a solution in our set K because K is compact and J is continuous. So we have a solution. And then we use, in order to find a solution, Alan-Weber iteration method, but I would not like to, so we need again the adjoint problem, but I would not like to detail this. And so we choose our starting initial guess, and our Lipschitz continuous stability estimate gives us this estimate in between the value of the solution, the solution operator R. So this is the solution corresponding to our initial guess and phi mesh. This difference can be bounded by a constant which depends on the constant we had in the Lipschitz continuity estimate. So this is somehow something we can compute. Okay, this is the numerical reconstruction. I don't want to enter in detail of the indexes, just to show you the reconstruction. So this was the ground truth in the first line, and then the second line, you see the reconstruction of the, in the first column, you have the phi 0, the initial datum, and in the second column, you have the phi capital T. And these are somehow some indexes that tells you that you are or not close to the real value in some norms, the one which were in the slide before. This was just for 15 days of evolution. So as you can imagine, if you have longer period, the reconstruction will be worse because you are going too much backward in time. So if you take 19 days, the things are not going so well. Okay, so let me just move to the second problem, even if it's late. Okay, so I will just give some differences with respect to the previous one. So the brain tumor model. For this brain tumor model, we always have an evolution for a phase parameter, which represents the tumor proportion. Pi equal to 1 is the tumor, pi equal to 0 the healthy cells, but its evolution is ruled by a Caniglia type equation, which was already introduced previously by Charlette, Agosti, and other people in order to model brain tumor growth, also in collaboration with the Besta Hospital in Milan. Then we take this problem and we want to tackle it from the optimal control point of view and also from the inverse problem point of view. So the system is a bit different with respect to the previous one. We always minimize an energy in our evolution. Here I also wrote the energy. So again, double well potential, gradient of pi square, epsilon is the thickness of the interface. Then you also have sigma square. So the nutrient, you don't have an interface in between nutrient. The nutrient is disgregated in between the zone where we have high percentage of nutrient and zone where we have low percentage of nutrient. And then here there is the coupling. So the term light blue is the one saying that the nutrient is, the tumor is going where the nutrient is higher, in the direction where the nutrient is higher, and the sky is the so-called chemotaxic effect. And this appears in the equations here. So you have this chi times sigma and also a transport term in the sigma equation, chi times the Laplacian of sigma. So here the equation for sigma is always a reaction diffusion equation, but with transport. So it's a bit more difficult, but still endable. In the equation for phi now is a Caniglia type equation, because here you see the Laplacian of the chemical potential, and the chemical potential is given by the derivative of the free energy with respect to phi, and you can see that there is a fourth order term in space for the phi. So this is a typical Caniglia type equation, but it's more difficult with respect to the usual one because on the right hand side you don't have zero. So this is the Caniglia equation comes from a mass balance, but you cannot have conservation of the mass in the tumor. The mass is growing and the mass is reducing depending on several factors, for example, from the nutrient. So on the right-hand side, you have the effects of the unbalance of mass, let's say. something which is making the tumor growing, the mass of the tumor growing or not, depending on other factors, which I don't want to detail now. So in this model, which was introduced the first time by Hawkins, Daroud, and collaborators, is particularly useful for us as analytical mathematicians, because here we have the same term, the same violet term on the right-hand side. And so what is concerned is not the mass of phi, but the mass of the sum of phi plus sigma, at least if you don't have these orange terms. And this is useful in some parts of mathematics. Let me just speak about the inverse problem, which is the most difficult one with respect to the previous one. So again, here we are able to prove backward uniqueness for the inverse problem. So as before, in particular, if you have regular data, so the phi 0 is in H2 and the sigma 0 is in H1. You see more regularity here because it's a fourth order in space equation, so it's reasonable to have more regular data. And we have again Lipschitz stability only in finite dimension subspace of our phase space. So again, the difference of initial values is estimated by a constant times the difference in norm of the solution at the time capital T. Here you don't have the prostate index because you have just brain tumor, so it's not meaningful to have the prostate index. So you have only two variables, but this is always a Lipschitz continuity estimate. We can prove that we have strong solutions, we have logarithmic convexity approach, and we can prove backward uniqueness as we did before. And as I told you, we have Lipschitz stability estimate if we start in finite dimensional subspaces of our space. Then again, we introduce a Tikhonov regularization. The difference here is that we solve the minimum problem where we have again the two L2 norms, so two quadratic terms, tracking type. But also here we have a regularized term which comes from the Ginzburg-Landau type of energy we have before. As you can see, you can recognize here there is the double well potential, and here the gradient of phi square and the sigma square, as it was in the energy. And this helps from numerical point of view in order to solve the minimum problem and to find explicitly the shape of the solution. Again, we are in the set of admissible set, and this is natural for, as I said, for Ginzburg-Landau type energies. We can prove that this Tikhonov problem has at least one solution, which solves this first order optimality condition. So these are the optimality condition for the initial data, which involves the initial data of the adjoint system, which I did not introduce, but these P and R are the adjoint system. So as we have seen before. Even if we have uniqueness in this H2 times H1, we decided to study the Tikhonov problem in the classical energy space because this allows us to have less expensive numerical discretization. And okay, skip the strategy of the proof. What we do numerically, we do the reconstruction only of the tumor phase because it's not meaningful to reconstruct the nutrient. This is more useful. And we use synthetic data, not real data for the moment, even if we plan to do it together with Policlinico, San Matteo, and Pavia, and reference of model parameters. And this is the case where we have regularization parameters. You can see we don't have exactly squares because we have regularization. And if the parameters are regularizing more, so you have higher values of alpha. Alpha was our regularization parameter in the Tikhonov functional. For higher values of alpha in the corner in the right bottom of the slide, you can see you have circles basically. So you start from squares, but you have circles due to these regularizing effects of the Tikhonov functional. And here you can see some longer time horizons, so with different more fine discretization terms for 90 days again. This is the initial condition, the ground truth in the middle, and on the right you have the final condition, and we refine the mesh just in between where it's needed, and then we can reconstruct the final condition, even if it's not the same, but okay, this is possible, and it is better, obviously, if we have higher values of our discretization time and index. So these are just the references for your convenience. So all these papers are in collaboration with Pierluigi Colli, Hector Gomez, Guglielmo Lorenzo, Gabriela Marinowski, Alessandro Reali, and also Matteo Fornoni, who was a PhD of mine in Pavia, now is a postdoc in Vienna, and Elena Beretta from Abu Dhabi, and Cecilia Cavaterra. They are the experts in inverse problems, and so we just collaborated with them. Abramo Agosti is the responsible, a colleague of mine in Pavia, is the responsible for numerical simulation in the brain model, while Guillermo Lorenzo is the responsible for the ones in the prostate tumor. So which are our conclusions, so our goals for the future? Here you can see some simulation for the brains, which I didn't show you before. So the differences between MRI and the digital twin of the patients. So what we would like to do is to get optimal personalized drug delivery plans in order to better attack the tumor, and in order to inform the clinicians how to work on this. Okay, and so what we could include in the model is, for example, to have multi-phases model, for example, to differentiate in between proliferating tumor phase and necrotic tumor phase. We didn't do it in this model. We have some analytical works on this, but not on inverse problems. We would like also to include mechanical effects, so for example, deformations of the tissues and anisotropies and so on. And with this, I conclude. I thank my collaborators that you can see also here in the picture, and I thank you for the attention.
Okay, thank you very much. Any questions from the audience?
Elisabetta, how are we doing? I'm pleased to
Fine.
have you. Yes, very nice talk.
Thank you.
I'm wondering, when you have this control variable in the control nutrient, is your model able to recede the growth of the tumor, or is just monotone increasing, or can we just go back in its size? Can you control the growth negatively, say?
Yes, as you have seen from the at least we can see it from the simulation. We cannot show we cannot have it analytically to show the shape of the tumor, because we have a phase field model and it's difficult to show it. But we, at least from simulation, we have seen that actually the tumor is reducing for some time. If we apply this S to the nutrient in the nutrient equation, and then so it's decreasing, the mass of the tumor is decreasing, and then it's increasing again. So there is a value, an optimal value, let's say, where is shrinking, and then it's growing again. While if we apply both therapies, is better. So it seems that the tumor is decreasing more. Another problem that we tried once was to take as a target a stable state for the system. So we impose in the control function to have a target like a minimum of Lyapunov functional in a way that when you reach this target, the tumor should not grow too much again. There are several stationary solutions, as you know, for these problems, because this is the double well potential and so on. But at least to prove that you are going towards a Lyapunov equilibrium, this could be something in order to ensure that you don't grow again later.
Great. Any other quick questions? I did have one quick thing. Your simulations seem to be in 2D. Would there be a big effect if you switch to 3D?
No, okay. We also have some simulations in 3D, but they are longer to be done, and so we don't have so many. But it's possible, yes, and they are not.
Great. Well, thank you very much. I think we're out of time.
You're welcome. Thank you.
I think the next talk's at 3:20, is that right?